Hello students all over the world. Once again you are welcome to our series of lectures on complex numbers. I am your lecturer, Professor E.O. Efang. This is the 6th lecture in this series, and the topic is the nth root of a complex number. Given a complex number in polar form, that is, given z equal to r exponent I theta, which can also be expressed as r into cos theta plus I sin theta. But for non-negative integer k, that is, for k equal to 0, 1, 2 and so on, cos theta is equal to cos theta plus 360k, and sin theta is equal to sin theta plus 360k. So we can therefore express z as z equal to r into cos theta plus 360k plus I sin theta plus 360k, or in exponential form as r exponent I theta plus 360k. Now let us raise both sides to power 1 all over n to obtain z to power 1 all over n is equal to r to power 1 all over n times exponent I 1 all over n into theta plus 360k. That is, the nth root of z is equal to nth root of r times exponent 1 all over n into theta plus 360k times I. Now let the nth root of z equals to zk, and 1 all over n into theta plus 360k equals to theta k. So therefore zk, which is our nth root of z, is equal to nth root of r exponent I theta k. And this we can express in terms of cos and cosine as zk equal to nth root of r into cos theta k plus I sin theta k. But we know that the nth root of a complex number has n values. That is, k will take value from 0, 1, 2 to n minus 1. Let us take example. Example 1. Find the square root of z equal to root 3 plus I. Solution. We recall that the nth root of a complex number z equal to r exponent I theta are given by zk equals to nth root of r into cos theta k plus I sin theta k, where theta k is equal to theta plus 360k all over n for k equal to 0, 1, 2 to n minus 1, and r is the modulus of a complex number given by the square root of root 3 squared plus 1 squared. Root 3 squared is 3, 1 squared is 1, 3 plus 1 will give us 4, and the square root of 4 is 2. Therefore, taking the square root of r, we have square root of r equals to square root of 2, since we are finding the square root of the number. And theta, which is the argument of a complex number, is equal to arctan 1 all over root 3, and this is equal to 30 degrees. So therefore theta k is equal to 30 plus 360k all over 2, where k is equal to 0 and 1. Note that since we are finding the square root of the complex number, that means n is 2, and k will stop at n minus 1. That is, k will stop at 1. For k equal to 0, we have t0 equal to 30 plus 360 times 0 all over 2. And that will give us 30 over 2, which is equal to 15 degrees. For k equals to 1, we have theta 1 equal to 30 plus 360 times 1, which is equal to 360 divided by 2. And that will give us 195 degrees. So therefore, zk is equal to nth root of r into cos theta k plus I sin theta k. Now for k equal to 0, we are finding z naught, which is equal to root 2 into cos 15 degrees plus I sin 15 degrees. From our previous work in trigonometry, we recall that cos 15 degrees is root 3 plus 1 all over 2 root 2, and sin 15 degrees is root 3 minus 1 all over 2 root 2. So our z naught is therefore equal to root 2 into root 3 plus 1 all over 2 root 2 plus root 3 minus 1 all over 2 root 2i. Opening this bracket, root 2 times this term will cancel root 2, times this other term will also cancel root 2, and this will then give us root 3 plus 1 all over 2 plus root 3 minus 1 all over 2i. And for k equals to 1, we are finding z1, which is equal to root 2 into cos 195 degrees plus I sin 195 degrees. Please note that 195 degrees is the angle in the third quadrant, and cos is negative in the third quadrant, sin is also negative in the third quadrant. And to find the trig ratio for the angles in the third quadrant, we have to subtract 180 degrees from that angle. So that is z1 is equal to root 2 into minus cos 15 degrees minus I sin 15 degrees, and this is equal to root 2 into minus root 3 plus 1 all over 2 root 2 minus root 3 minus 1 all over 2 root 2i. Opening the bracket, root 2 will cancel out to give us minus root 3 plus 1 over 2 minus root 3 minus 1 all over 2i. So these are the two square root of that complex number. Z naught equals to this and z1 equal to this. Example 2. Find the cube root of the complex number z equals to 2 plus 2i. Solution. Again, we recall that the nth root of a complex number z equal to r exponent I theta are given by zk equals to nth root of r into cos theta k plus I sin theta k, where again theta k is equal to theta plus 360 k all over n for k equal to 0, 1, 2 to n minus 1. Please note, in this case, since we are finding the cube root, our n is 3. And our modulus r is equal to the square root of 2 squared plus 2 squared. That's square root of 4 plus 4, which is equal to square root of 8. Now, let us find the cube root of our r. So the cube root of r is equal to the cube root of square root of 8. We can interchange the cube root sign and the square root sign to obtain the square root of cube root of 8. But we know that the cube root of 8 is 2. So this will give us square root of 2. Now the argument of a complex number theta is equal to arctan 2 all over 2, which is equal to arctan 1, and arctan 1 is equal to 45 degrees. So therefore our theta k is equal to 45 plus 360 k all over 3 for k equals to 0, 1 and 2. Note that since n is 3, our k will stop at n minus 1, that's 3 minus 1, which is 2. So for k equal to 0, our theta 0 is equal to 45 plus 360 times 0 all over 3, and that is 45 over 3, which is equal to 15 degrees. For k equals to 1, we have theta 1 equals to 45 plus 360 times 1 all over 3, that is 45 plus 360 all over 3, and this will give us 135 degrees. And for k equals to 2, we have theta 2 equals to 45 plus 360 times 2 all over 3, that is 45 plus 720 all over 3, and this will give us 255 degrees. So we recall that our cube root zk is equal to cube root of r into cos theta k plus I sin theta k for k equal to 0, 1 and 2. So for k equal to 0, we are finding z naught, which is equal to square root of 2. Remember the cube root of our r was square root of 2 into cos 15 degrees plus I sin 15 degrees, and this is equal to root 2 into root 3 plus 1 all over 2 root 2 plus root 3 minus 1 all over 2 root 2i. When we open the bracket, root 2 will cancel out to give us root 3 plus 1 all over 2 plus root 3 minus 1 all over 2i. Next, for k equals to 1, we have z1 equals to square root of 2 into cos 135 degrees plus I sin 135 degrees. Since 135 degrees is the angle in the second quadrant, and cos is negative in the second quadrant while sine is positive, and to find the trig ratio for the angle in the second quadrant, we have to subtract the given angle from 180. So this will give us square root of 2 into minus cos 45 degrees. That's subtracting 135 from 180 will give us 45 degrees. And since cos is negative in the second quadrant, that's why we have negative sign here. Then plus I sin 45 degrees. This is equal to root 2 into minus 1 all over root 2. We recall cos 45 is 1 all over root 2 plus 1 all over root 2i. Sin 45 is also 1 all over root 2. Opening the bracket, root 2 will cancel out to give us minus 1 plus I. So next, for k equals to 2, we have z2 equals to root 2 into cos 255 degrees plus I sin 255 degrees. 255 is the angle in the third quadrant. Cos is negative in the third quadrant. Sine is also negative in the third quadrant. To find the trig ratio for the angle in the third quadrant, we have to subtract 180 from the given angle. So that is root 2 into minus cos 75 degrees minus I sin 75 degrees. From our previous work on trigonometry, we can find cos 75 and also sin 75. So this will then give us square root of 2 into 1 minus root 3 all over 2 root 2 minus 1 plus root 3 all over 2 root 2 I. Opening the bracket, root 2 will cancel out to give us 1 minus root 3 all over 2 minus 1 plus root 3 all over 2i. We have come to the end of lecture 6. Thank you for watching. and keep on watching. I remain your lecturer, Professor E.O. Efan.